So from those two demonstrations, you should be able to come up with these conclusions, or this is really the conclusions that we came from the demonstrations. That planes defined in three space with 1 point and two direction vectors, and we saw that here we've got 1 point. Well, we've actually got 3 points, but and two direction vectors are enough to define this green plane. But you could, so as soon as you've got 1.2 direction vectors, you can define it. But technically, you could get away with just having 2 points and some independent direction vector. So if you just had 2 points separate that are on the plane, you can connect those two and get one of the direction vectors, and then the other independent direction vector that didn't include these 2 points would be the second direction vector. And then you would have more than enough to get 1 point and two direction vectors. So you'd have 2 points, and then when you find the vector between these 2 points, there's one other vector, and then another independent vectors gets you your 1 point and two direction vectors. Or you could just start with three non-collinear points, meaning they're not in a straight line. If they're in a straight line, it can't define a plane. It would define, you need 3 points that are not in a straight line in order to find a plane. And actually, when we think back to this is actually how I started. Okay, if you actually look here, you see you've got vector point A, B, and C, and what I did was I connected those vectors, or those points, to get one of the vectors, connected two other points to get two other vectors, and then that was enough to define the plane. All right, so these last two are possibilities to define a plane only because you can get to this standard of two direction vectors and 1 point. If you've got 3 points, you can add two of them together, or take two of them to get one vector, take another two and get another vector, then you've got this. All right, so you've seen all the demonstrations and all the visuals. Now let's see the math behind this. So we're going to look at this example here. And in fact, this example replicates what we just saw on the GeoGebra website. So let's actually look at it. So we've got these 3 points. So the points are just A, B, and C. A, B, and C. So they're just laying there. And if you're given these 3 points, so pretend we don't have the graph, we don't know what this looks like. You're given the 3 points, you need two direction vectors. Well, how are you going to get the two direction vectors? Well, one of them can come from going AB and doing B minus A. And the second one can come from connecting these two and getting D2. Now, of course, you could have done BC. That would be equally fine. You would get a third different direction vector, but we just need two of them. So why not just use these two? So AB came from B minus A. So if I subtracted this, -2 minus 5 is -7. 3 minus 2 is 1. -6 minus 6 is -12. Oh, sorry. Okay. And that's D1. D2 is C minus A. So 4 minus 5 is -1. Oh, -1, and then -5 minus 2 is -7, and -3 minus 6 is -9. And in fact, you'll notice that those are the exact two vectors that we had there. So there's the first one, 7, 1, -7, 1, -12, and the second one, -1, -7, -9, and there they are. Okay, so there you got your two direction vectors, and we've got our points. So we've got everything we need. Now we got to come up with the equation of the plane. So if you think back to equations of lines, there was all sorts of different ones. There was a general equation for a line, a vector equation for a line, symmetric, parametric, all that sort of stuff. Well, all of those exist for equations of planes. And the good news is they look almost exactly the same. So let's start off by doing a general equation for this plane, okay? And if you think back to the general equation of a line, it looked like this. We had the x, y, z, and then you took a point and you added your direction vector, a scalar multiple of that direction vector. That looks like a line, but we're talking about a plane. And planes have a point and two direction vectors. So you have another addition of the second direction vector with a different scalar multiple letter. Okay, so we define the general equation. Any point can be found by any given point plus a scalar multiple of d1 and a scalar multiple of d2. Now, I used the first point just because it was convenient, and this direction vector and this direction vector. You could have used this point and still been defining the same equation for the same plane. And like I said, you could have gone off and found like D3, a different direction vector. So there's lots of possible correct answers. And like I mentioned in the other unit, you don't want to just go off and do crazy ones, and then it's difficult for me to see which direction vectors you use. You want to try and use the standard ones. So I'm going to try and use like AB and AC all the time so I get these direction vectors. And remember, you could have done any scalar multiple of this. So you could say negative 100, negative 700, and negative 900. And that would be a legitimate direction vector to describe this equation. But don't get silly with it. It's best if you just use the given point here. I'm going to use the first one and the two direction vectors. But great, isn't it great how this looks an awful lot like the equation of the lines that you just finished studying? But now it's an equation of a plane, and it's got a point and two direction vectors. All right, so the general equation looks like this. Is there a vector equation? Sure. If you remember, the vector equation comes from subtracting this and bringing it over to the same side. This is a positive point. If I bring it over here, I'm going to subtract. So it's going to be x minus 5, y minus 2, and z minus 6. And all of that looks the same, equals, and then what are you left with? Well, you're left with the two direction vectors, the scalar multiples of the two direction vectors. Next, when we were studying lines, the next thing we did was a symmetric equation. Well, you can't do symmetric equations of planes, okay? You can't have all of these things because you've got two direction vectors. So remember, symmetric equations, you took this negative 7 and you divided it, and it was like x minus 5 over negative 7. And this divided by that, divided by that. Well, you've got two things, so how can you divide by it? By both of them. It doesn't work that way. So it turns out there is no symmetric equation for planes. There's a general equation, a vector equation, no symmetric, but there is a parametric equation. And the good news, again, the parametric equation feels just like the parametric equation of a line. It describes how each coordinate is found, the x, the y, and the z. Oops, I gave you that. Well, so let's just look at the x. The x comes from taking the x coordinate, so 5, plus the scalar multiple of this is negative 7k plus negative 1l. So there's your 5 plus your negative 7, or just minus 7, plus your negative 1l is minus l. So y, sort of gave you a sneak peek there. The y comes from 2 plus 1k plus negative 7l. So we'll just say minus 7l. And then can you predict what z is? Z is going to be 6 plus, well, minus 12k minus 9l. And there it is. So again, great news. This looks just like a parametric equation of a line, except a line is a point and one direction vector. A plane is a point and two direction vectors. So you have this. Okay? All right. So far, so good. And like I said, that looks just like what we have here. You can see those vectors. All right. What else do we have? Well, before we go any further, let's consider this thing called the normal. Now, we talked about the normal of a line being one that is perpendicular to the line. Well, a normal to a plane is perpendicular to a plane. So let's actually think about what that would look like. So I'm going to go back to our visual here. So here's our graph. And a normal is going to be a perpendicular line to that. So I've actually got it set up here, and I'm going to just reveal it. And look, there it is. So you see we're kind of looking down the barrel of we're looking right down, oh yeah, look at that. Right down the equation of the plane. You can't even see the plane, it's so skinny. And there's the normal, which is perpendicular to it. Of course, it goes off in both directions. It'll be perpendicular that way and perpendicular that way. Okay, and we can twist this around, and you can see there's another example of how it's perpendicular to it. Okay, so this normal can be used to describe the plane as well. So sure, you want your point and your two direction vectors, but guess what? This normal is going to look the same no matter where you are on that plane. It's perpendicular. So right now you see the normal is going through A. Okay, so I'm actually going to just show you here. If I change this and I go here and have it going through point B, push enter, look, doesn't it look exactly like the same normal? It looks just like the same normal, and it's still doing the same thing. It's still perpendicular to the plane. It's just going through at a different spot. And I could even have it go over to C. There it is. Okay, so this normal can actually be anywhere on that plane. And imagine if I was holding the piece of paper up in front of you and I took my pencil, which was my normal, and it's perpendicular to the plane, it would stick with that plane no matter how I twisted it around. It's perpendicular. So the normal can be used to describe the plane, just like you use the normal to describe lines. Okay, so the catch is, how am I going to figure out what this normal is? How am I going to figure out that equation for this normal? Well, one characteristic of that normal, I'm going to put it back at A, just so it looks kind of similar. One characteristic of A, of the vector, excuse me, the normal that goes through A, is that it is perpendicular not only to the plane, but it's also perpendicular to the two direction vectors. So that sounds familiar. I need a vector that's perpendicular to two vectors. Well, if you think back to the beginning of vectors and our first unit of vectors, we actually did this. Remember, you were stuck with this idea, give me a vector that's perpendicular to two other vectors, and you found the right-hand rule. Remember that? The right-hand rule was demonstrating, and you found out if the two vectors were on the whiteboard, the right-hand rule might tell you that the vector is coming out of the board or into the board. Okay, well, that is a vector that is perpendicular to both. And where does the right-hand rule come into? It comes in when you take the cross product. So the cross product of this vector and this vector will be the normal. Okay, so let's just look back at our notes here. Then, in order to find a normal that is perpendicular to the plane, it must be perpendicular to both of them, which means I can take their cross product. So the cross product will get us the normal. Okay, so let's see why that's so helpful. So let's actually figure out what the cross product is between the two direction vectors. So let's just remind ourselves, we're still doing this question, so we're going to use these two direction vectors, and we're going to find the normal. Okay, so from the example, there's the two direction vectors. We're going to do their cross product. So I'm going to speed this up a little bit. There they are, the cross products. Okay, and you're going to scratch out the first two, and then you do your down products minus your up products really quickly. Multiply this, we get -9 minus a positive 84, excuse me. Um, Sorry, that's a 7. 7 times, I look like a 3, excuse me. 7 times 12 is 84. A negative times a negative is a positive, and we're subtracting it. -12 minus 1 is, or times -1 is 12. Minus, oh no, this is a positive 63, and then a positive 49 minus a -1, or minus a -1 is plus, and we get then that the cross product is -93, -51, and 50. Okay, so if you want to take some time to look at that, you can. But trust me, the cross product of these two is this, which means the normal is -93, -51, and 50. And we're getting pretty good at finding cross products, so we can find the cross product pretty quickly. So where does the normal come in to this equation of a line? Where does it come in? So I had a general equation which used the two direction vectors, vector equation that did two direction vectors. There was no scalar equation, or symmetric equation, excuse me. There's a parametric equation, but there is a scalar. Okay, so I'm just going to bring all these back. Okay, so there is a scalar equation. Just bringing this all back. There is a scalar equation. And if you remember, the scalar equation of lines was found by taking the normal, and it became the coefficients of your equation. So if the -93 is in the x position, it's -93x, and then minus 51y, and then a plus 50z, plus some constant equals 0. Now, when we were doing with lines, that constant was a c, but now we're doing it with planes, so the c positions here, this is going to be the d. And if you recall, to figure out what this constant was, this d, we had to take a point and sub it in. So we're going to take a point from the plane. So let's use the a point. There's the a point 526. Let's use that. So we're going to substitute that a point into our equation. So when you sub in the x equals 5, the y equals 2, and the z equals 6, we get negative 465 minus 102 plus 300. I can tell you that's like negative 267. And then if you bring that negative 267 over here, you get the d value is 267. That means the scalar equation for this plane now is this. But remember, scalar equations, we don't like to have a negative. They're the same as standard form, so we don't want to have a negative at the beginning. So if I multiply or divide everything by negative 1, this becomes a positive, this becomes a positive, this becomes a negative, this becomes a negative, and there we go. There is our scalar equation, and you can see the normals. So this normal, 93, 51, and negative 50, is just a scalar multiple of this normal. It's just going in the opposite direction. And if we go back and look at our graph, you'll see that all of this numbers actually is popped up in the calculations. The GeoGebra did these calculations to get the equation. So look, there's the same one. Now it has the negative here. It doesn't care about the negative at the beginning. We do. But there's the exact equation that we just did by hand, and we got it here. And then look at this equation here. This is the perpendicular line, that black perpendicular line. And to draw it, you see, look, there's the normal. Negative 93, negative 51, and 20. Or 50, excuse me. And this is the negative version, which is doing this half. And if I had the other version, it would be doing the positive half or the other half. Okay? All right. So we've done then general equations, vector equations, parametric equations, and scalar equations. And those are all the different equations for planes. All right, let's move on to another example. Here, I'm going to rewrite now. So I'm giving you a vector equation, or sorry, an equation of a plane, and this looks like general equation. Let's just go back and check. Yeah, general equation. There's a point plus two direction vectors. Yes, that's general equation. Point and two direction vectors. I want it in scalar form. So I'm going to do this without any help. I'm just going to use my algebra skills to be able to do this. So I need the normal. How do I get the normal? It is the cross product of the two direction vectors. Where are the two direction vectors? They're right here. They're really easy to see. There's the first direction vector. There's the second direction vector. So I've called them D1 and D2. I need to do their cross product. Again, I'm going to speed through this. Trust me that the cross product turns out to be negative 6, negative 3, and 1. All right, once I have those cross products, those become the coefficients of my equation. So there's negative 6x minus 3y plus z plus d. I'm going to deal with a negative in a second. I need to figure out the d. I need to put in a point. No sense searching for a point. There it is right there. So I'm going to substitute it right in. So the x is 1, the y is negative 4, the z is 3. Plug those in, and you'll see it's negative 7 plus 12 plus 3. So I think that's a 9. And then if you bring it over here, it becomes negative 9. And so my equation, I figure out the d is this, negative 6x minus 3y plus 7, or plus z minus 9, but I don't like it in that form. I want to get rid of the negative in the front, so I divide everything by negative. That becomes negative, that becomes negative, that becomes positive, positive, negative, positive, and there is my equation. Okay, so to come up with a scalar equation, cross product, get the normal, put the normal as the coefficients, sub in your point to get d, and make sure it's positive. So I can actually check this. So let's just go back to GeoGebra here, and I've got this set up here. So here's the point and two vectors. Okay, so there's the point and the two direction vectors that are defining this plane. So I can ask GeoGebra to get me the plane. So I'm going to type in plane, and you see all the different ways that you can find planes. And look, here you go. A point and a line. Or sorry, 3 points. A point and a vector and a vector. Okay, the line would have a point and a vector on it. A point and two vectors are 3 points. I'm going to do this one. I've got a point and a vector and a vector. So the point is A. The vector is vector S. I've just called it S, and comma, and get rid of all this other stuff. T, and boom, there it is. There's the equation of the plane that's described by those two direction vectors and the point. And if you look closely, there is the equation that we got as an answer. Okay, negative 6x minus 3 plus 7 minus 9 or equals 9. Okay, and it just doesn't have the negative in the right spot, or it just has a negative here, which is fine. And if you look closely, you can see that it's calculated by doing S cross T. This is another notation for cross product. So even it knows to get the normal, I had to do the cross product, and it did the cross product and got the numbers. Okay, all right. So there we go, moving from scalar equation, or from general equation into a scalar equation. Last example. Find the parametric equation of this plane. All right, so the first thing you're going to notice here is this notation. So if you remember back to lines, we used a little L to describe lines. So we had like L1, L2, L3. To describe planes, we use the Greek letter pi. So for starters, this pi is not 3.14. It's just a Greek letter. Once you get into more advanced mathematics, you see that pi is just a Greek letter. It's not always 3.14. So we use this symbol to describe planes. We use Greek letters to describe planes and regular letters to describe lines. So we're going to use pi 1. Okay, it has nothing to do with 3.14. Okay, you'll see that this equation is in scalar form. Okay, it's in scalar already. We need to put it in parametric. So to put it in parametric, well, if you think back, let's go back and look at parametric. Parametric had a point plus two direction vectors. So we need a point and two direction vectors to put it in parametric. So let's look at the question. The question, though, only gives us this much information, and we need two direction vectors and a point. So first, let's try and tackle how to find the direction vectors. Well, this doesn't tell us direction vectors, but it does tell us the normal. Remember, we just discovered the normal is the coefficients of the x, y, and z. So the normal is going to be a 3, a 1, and a negative 2. So the normal is the vector 3, 1, negative 2. That's great. The normal is perpendicular to our plane. But I need direction vectors that are on the plane. Well, if they're perpendicular to the normal, I can get all sorts of vectors that are perpendicular to this one. Think back to unit 7, I think it was, where we found a shortcut to get perpendicular vectors. Remember, we could take one of these and make it 0 and switch the other two and make one of them negative. So if I made this 0 and switched the y and z and made this one a negative so it becomes a positive, there's a vector that's really quick and easy that is perpendicular to it, which means it must be one of the direction vectors or a direction vector that's on our plane. I could make the middle one 0 and switch the first and last. And I switched the first one here and put it at negative, put the 3 in the back and made that one negative. There's a whole bunch of different ones that I could have used, and you might choose to maybe switch the first two and write -1, 3, and 0. That would have been correct as well. All of those would be possible direction vectors. You can see how there's so many of them. I think there's going to be 6 using the shortcut, but there's tons others. There's tons of direction vectors. And I'm not going to be upset if you choose different ones than I do. But I've chosen these two. All right, great. Now I've got two direction vectors, but now I need a point. Well, a point is any x, y, and z value that satisfies this equation. So I could put in x equals 1 and y equals 7 and try and figure out what z is, or I could put x equals 2 and say that's 6 and all that sort of stuff, and try and guess and check values for x, y, and z that will equal 0 or equal 1, excuse me. Well, here's a great way. So to get a point, I could kind of cheat. What if, since I can choose any values for x, y, and z, as long as they satisfy this, why don't I put a 0 here and a 0 here and solve for y? So if I do that, you see I get a 0 here and a 0 here, and if I solve for y, I get y equals 1. And so a point that satisfies this equation and therefore is on the plane is 0, 1, 0. It's actually the y-intercept. The y-intercept's when the x and the z equal 0. Okay, so that was a neat little trick to get a point on the plane. Now, I could have maybe made this 0 and this 0, but then I'd have 3x equals 1, and I would divide and I'd get 1/3. So 0, 0, 1/3 is another point that's on there, or put a 0, or sorry, 1/3, 0, 0. I could put a 0 here, and divide this, and it'd be 1 over -2. So that's another point. But you see, if I put a 0 here and 0 here, the y is really easy. Okay? So anything you choose to get three things that satisfy this equation will be a point. All right. So with some logic here, I've found two direction vectors and a little bit of fiddling to get a point. I have everything I need for a parametric equation. So I'm going to use the same label because it's the same plane. So pi 1. And I'm going to do the x coordinates, the y, and the z. Okay, the y and the z. So the x comes from, I'm actually going to do the z first. So the z is 0 plus 1k minus 3l. Okay, so 0 plus a scalar multiple of d1 and a scalar multiple of d2. And I just happen to use k and l. All right, and there's a 0 out front. What about y? 1 plus 2k plus 0l. So 1 plus 2k plus 0l. I'm not going to have the 0l. And then what about the x? The x comes from here. It's 0 plus 0k, so there isn't a k, minus 2l. So 0 plus 0k and minus 2l is just plain old 2l. And that is the parametric equation of this same plane right there. Okay? You might have a slightly different answer because you might have found a different point and you might have found different direction vectors, but you would get the proper and exact, you would get an equally correct answer. And I wouldn't be upset about that if you were slightly different than mine. Okay? All right, so you've seen lots of demonstrations today and lots of math that supports those demonstrations. So I really hope you've enjoyed your introduction to the equation of planes.